So, let us try to understand non-linear regression now. By non-linear I mean that let us say we have some hypothesis that the actual the relation between features that should explain y is not necessarily linear. It is not W transpose x, but then some other complicated relation, maybe height and weight are your features. You want height square plus 3 times weight minus weight squared or something like that, that best explains our label y, for example, right. So, then your linear regression will fail because it cannot capture these either the squared terms, or if you had a cross term like height into weight, which makes sense, which is important to explain your y. Still linear regression would not be able to capture such relationships. You can still run linear regression, but then even the best W will make perhaps a lot of error in your training set and your validation set also. So, how can we do non-linear regression? Remember our idea for moving from linear PCA to non-linear PCA was via this notion of kernels. We will do the same thing here. The trick there was to write the optimization problem of PCA on what you wanted to get from PCA in terms of the dot products between data points, and once we were able to do that, then we could use a kernel matrix to replace this dot product, and then it would mean as if we went to a higher dimension and did a PCA. That was our kernel PCA algorithm. So, we are going to do something like this here as well. So, it is as if you want to map your data points to a higher dimension and then learn a linear model in high dimension, a regressor, but then you do not want to explicitly compute these high dimensional mappings. So, how can we do that? Can we do that? We can do that if our regression solution somehow can be written in terms of the dot products between data points. But what is the regression solution itself? The regression solution itself is XX transpose pseudo inverse XY. So, this is the matrix, this is the vector that we have, and as it stands it does not depend on the dot product directly, right. So, XX transpose is a D cross D matrix. A dot product matrix would be an N cross N matrix where you have pairwise value for every pair of data points. That is not there here. But now we know that this W star from our geometric considerations also, and also by thinking about this a bit, that our W star, the solution to this problem of linear regression must lie in the span of the data points, right. So, let me put that down and then try to explain that, right. So, W star, this is the first point that we will note, must lie in the span of data points. Now, why is that true? Right. So, what does it mean to say W star lies in the span of data points? So, you have a bunch of data points D dimension. So, then W star is also a vector in D dimension. I am saying if all the data points were lying on a plane in 3-dimensional space, then W star will also be on the same plane, right. So, let us think of this in pictorially. Maybe you have a 3-dimensional data points, but then necessarily not all points are in 3 dimension. Let us say there is some, maybe I will use a different color, maybe there is some 2-dimensional plane sitting inside this 3-dimensional space, which is where our W star actually lies in. That is where our data points lie in, not W star yet. Okay. So, let us say all our data points are 3-dimensional points, but then they effectively are lying in some 2-dimensional plane, let us say. Now, now the question is, will our W star also lie on this plane, or can W star lie outside this plane? Now, let us say W star, for the sake of argument, let us say that W star was lying outside this plane. Maybe this was our W star. Now, remember W star is the one that minimizes the sum of squared error, right. So, W star transpose xi minus yi squared is as small as possible among all possible W's. Now, if this W star was actually out of this plane, right, so maybe it was not on this plane, then let us now look at the following new W that I give you, which is the projection of this W star onto this plane. That is the closest point of W star on this plane. Now, let us call this guy as W tilde. Okay. Now, let us ask the question, what can we say about W tilde transpose xi minus yi? Well, how does this compare to this guy, right? So, is this of course, it cannot be less than this, strictly less than this, because by definition we are assuming W star has the smallest value because it solves this problem. So, the right hand side cannot be less than this, but what is the actual relation between these two, right? Now, if you think about this, right, so now W star's projection onto this plane is W tilde, right. So, now which means that there is this, okay, maybe I should do a different color. So, there is this vector plus this vector, that is W star can be written as W tilde plus W tilde perpendicular, right. So, the one that is perpendicular to W tilde, and then if I add these two things I get W star, right. So, now W tilde perpendicular is perpendicular to W star to this plane basically, right. So, because it is you are projecting W onto this plane, so which means W tilde is perpendicular to this plane. So, it is perpendicular to all the points on this plane, it is orthogonal to all the points on this plane. So, which means that W transpose xi, W star transpose xi is W tilde plus W tilde perp transpose xi, which means it is same as W tilde transpose xi plus W tilde perpendicular transpose xi, but then because this is orthogonal to this plane, xi is in this plane, so this guy is 0. So, this is for every I, right. So, for any data point, the dot product that W star makes with respect to the data point is exactly same as the dot product that W tilde makes with respect to this data point, right. So, which means that W star transpose xi is same as W tilde transpose xi, which means that the prediction of W star and W tilde for all the data points are exactly the same, which means that the error that both of these will suffer is exactly the same, right. So, with respect to the training data, which means I might as well use W tilde as opposed to W star, right. So, as long as I have W tilde, I am good enough, right. So, what I can then say is that, well, without loss of generality, I can assume that the original W star that I have actually lies on the plane or in general in the span of the data points itself, right. So, I can start with such a W star because that W star is good enough for my predictions, and so I will use that W star. Okay. So, what does that mean? That means that W star equals some linear combination of your data points, right. So, your data points are in a plane, and so linear combination of this data point should have given W star, right. So, it is some x times alpha star for some alpha star in Rn, right. So, Rn, because there are n data points, and we have a D cross n matrix which is x. So, you are taking all the vectors in the data set, weighing them using alpha star I for the ith data point, adding them up, and then you will get W star. But remember, we also know W star is just xx transpose pseudo inverse xy. This comes from our gradient analysis, right. So, we took the gradient, set it to 0, and then we got W star is this. So, this means that x alpha star equals xx transpose inverse xy or pseudo inverse. I mean, I will keep saying inverse, but then it also means pseudo inverse. Okay. Now, what we want to do is we will kind of try to get rid of this xx transpose. So, we will pre-multiply by xx transpose on both sides to get xx transpose x alpha star equals, well, again xx transpose into xx transpose pseudo inverse xy. This is to cancel out this guy. So, these two guys kind of cancel out because that is the property of pseudo inverse. If you multiply the matrix with its pseudo inverse, you will get an I, right. So, this is this just means we have x transpose times x alpha star equals xy. This is where we are right now. So as you can see, the whole goal is to somehow write it in terms of x transpose x, right? So we have x transpose x here, but then there is also an x sitting on the other side. So we can simply say that we'll pre-multiply this whole thing by x transpose. Let me use a different color to show the difference. Maybe I'll use green. X transpose times x transpose x alpha star should be equal to x transpose xy. Now we have something that is nice in the sense that we have x transpose x occurring twice here and occurring once here. So which means this whole thing can be written as x transpose x square times alpha star is x transpose xy, which means x transpose x is our kernel matrix, which we can, let's call this as K, define this as K. So then this just means we have equation K square alpha star equals Ky, or in other words, if K is invertible, so then we can simply say alpha star is just K inverse y. So basically this simply means that what is the use of this, right? So what are we saying? We are solved for alpha star, where W star is how you should combine your data points using alpha star to get W star, and we are saying if you use a general kernel matrix, then the way to combine is given by the inverse of the kernel matrix times y. Now what is the use of this? The whole point of doing this is that now when you do prediction, right, so if you have a new data point, let's say for some x test, if you have a new data point x test in d dimension, then the kernel would tell you that, well, I need W star transpose phi of x test, right? So I have to map my x test to high dimension and then take a dot product with W star, which is the best W star, which minimizes the squared error of all the data points mapped to the higher dimensional space, right? So W star would actually be the minimizer or the argmin over sum over I equals 1 to n phi of xi minus yi squared, right? So this W star is like you are given a data set, you have mapped every data point to high dimension, and then you are solving a linear regression problem in the high dimension, you get W star. So now which means if you get a new data point x test, you map the data point to high dimension and then dot it with W star. However, we don't want to do this, right? So meaning we cannot afford to do this explicit mapping. That's the theory of kernels, as we have seen before. So can we make this prediction without explicitly using phi? Well, that's what our alphas will help us do. So this is by the virtue of the fact that W star is just sum over I equals 1 to n alpha star I phi of xi, right? So that's what it means to say W star is a linear combination of data points in high dimension. Now this transpose phi of x test. This is our prediction. But now this can be gotten as sum over I equals 1 to n alpha I star the kernel evaluated at xi comma x test. Alright. So you have a kernel matrix, kernel function, which given any two data points evaluates the dot products in high dimension, which we can do using this, and then alpha I star is simply got by solving K inverse y, where K itself is just an n cross n matrix where you evaluate the kernel for the data set, like how we did for PCA also. The extra thing that appears here is the y also matters now. Of course, it should matter because it's not PCA, right? It's unsupervised, right? So this is supervised. So the label should also matter, and so the y also comes into the picture here. So basically then how would you do non-linear regression? The algorithm is very simple. So you are given a bunch of data points, you are given a kernel function, Now evaluate the kernel functions on all these data points to get the matrix K in n cross n matrix. Now compute alpha star as K inverse y. Now once you have alpha star for a new data point, any data point x test, you simply compute prediction as sum over I equals 1 to n alpha I star times the kernel function evaluated at xi and x test. It is as if asking, you can think of the kernel function as how similar are these two data points. That is what the kernel function is in some essence doing. So then this is saying, given a new test point, I am seeing how similar is this test point to each of my training data points. That is what the kernel evaluated at xi comma x test is saying, how similar is this new point to each of the training data points. But then how important is this training point to the w star, that is given by alpha I star. So alpha I star says how important is ith point towards w star. Now the K of xi comma x test says how similar is x test to xi, right. So you might be very similar to a data point which may not be so important for w star, right. So it's the product of these two things that matters in our prediction, and then you sum it up over all data points. So now by choosing different kernels, which we have seen earlier, quadratic kernels, cubic kernels, Gaussian kernels, your favorite kernel, whatever you want to pick, now you can solve the regression problem in any higher dimensional space. So that's the power of kernels. Now basically what we have managed to do is we have kind of kernelized our linear regression problem to solve for non-linear regression as well. Okay, so this is the this is about the relationships between features and how they explain the variables. So far we have looked at three different aspects, right. So one is the geometric consideration of what does it mean to say we have a w star, and we explained that as projection of labels onto the features, subspace spanned by the features is just your x w star. Then we looked at computational considerations. We came up with the stochastic gradient descent algorithm, and now we are saying, well, if you want to if you want to capture nonlinear relationships among features that explains the labels, then use kernel regression. This is what is called as kernel regression, as how PCA to kernel PCA, regression to kernel regression. Sure. Okay, so these are some aspects. So we'll look at one more aspect now about linear regression, which is another powerful aspect which will actually lead us to several more interesting variants of this linear regression problem itself, and that is to introduce something that we have not so far seen in linear regression, which is introducing probability into linear regression. Right now everything is deterministic. So what happens when you look at linear regression from a probabilistic viewpoint, which is what we'll see next.